as serious. So let me talk about differential equations. And maybe I could start by asking, perhaps I could ask by the show of the blue hands, how many people have taken like a real differential equations class, like maybe 1803 or an analog of 1803? So I'm assuming that it's not required for this class, and I'm going to start from the beginning. But I'm just curious. So here, let me see how I can. All right, so keep your hands raised.
Three people have raised their hand.
3 out of 13, right, have raised their blue hands, right? And Jeremiah has also raised his real hand too. So, okay, so 3 out of 13. So, okay, it keeps changing from 2 to 3. People are putting their blue hands down. Yeah. So as I expected, a minority of you. So I'm not going to assume any background in differential equations. But if you do have a background in differential equations, I'm going to want to believe or hope, you can tell me when this is all over, that the perspective that you'll see is like nothing you might have gotten from your differential equations class, maybe. I mean, it won't be unrelated, but it'll be a new perspective, I hope. All right, so let's see. So you know that lots of people are solving models these days. There's a whole alphabet soup of them out there. There's SIR, there's SEIR. If you go to Wikipedia, let's do that together. If you go to Wikipedia, right? So everybody sees my screen just fine? If you go to SER and pick out the right one, which is the compartmental and epidemiology, you see there's a whole alphabet soup. There's SIRD, MSIR, SEIR, SEIS. You never know even where to start, right, when you have so many choices. So it'd be sort of good to disentangle that. But if I had to kind of make it simple right now, if you just want to, like, you know, if you've been following the press, you probably see that like the SIR is sort of the basic simple one that a lot of people start, you know, like that's the one on training wheels, I think it's safe to say. And, you know, and then I think the next step, the one you graduate to is SEIR. That's the other one I've seen a lot of. And I can't say I've really seen these other fancy ones quite as much. They're all variations on the same thing, so don't get all caught up in this. But just to get you all started, it's the SIR and the SEIR are the two that you see the most. All right. So, and you know, we'll get into this in a minute, but if you're just wondering what all these letters are, what is happening is that that populations are, as you'll see in the homework, populations are divided up into compartments, and people basically can move through these compartments. And so in the SEIR model, you know, you start out being susceptible to infection, right? And so that basically means you're healthy, you're uninfected, you're unexposed, but if you bump into somebody, you could be in trouble. Then you move to the exposed category, which means that you're not yet infectious, but you will be in a little while, okay? And then there's the actual infectious, where during a later time period where you actually can infect another individual. And then hopefully at the end of this period, you recover. I guess another possibility is you may pass, but hopefully you recover, right? So they're actually, I'll get into all of these things a little bit more, but just to sort of say these words right now. And of course, the SIR model doesn't have the exposed category, so it's just a simpler model. So you're susceptible, you're infectious, you recover. All right, but let me sort of go a little slowly. I'm going to get back to all this, but let me just mention that, you know, we do teach differential equations at MIT. Myself, I'm in the math department, so many of my courses start with 18, the ones I teach. I haven't taught 1803 as a professor. I've TA'd it a long time ago. But you can actually look, here's the website for 1803. And if you look through the topics in this class, there's a lot of very traditional topics. Basically, a lot of the differential equations that you'll solve in 1803 are what I might call the pre-computer differential equations, where you basically solve these symbolically, or you learn some properties of the solutions analytically, but not so much what really is happening more and more by researchers today, which is numerical solutions. If I was looking at, this semester, so I was just looking at it today. At the very end of the semester, which is over here, let's see, here we go. These are all traditional things. Like I said, all pre-computer, bump, 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 all good stuff. But the numerical methods, it seems to be sort of at the very, very end. And of course, they do an SEIR model. So, this one is done in another computer language. It's not done in Julia, but we'll do it in Julia. Oh, here's the actual schedule. So it looks like, some of you may actually be in this class, but let's say May 4th. Okay, so it looks, oops, that's not what I wanted to do. Where did it go? Here, it went. Nope, that's not it either. Where did it go? I'll just do that again. Sorry. I wanted to see, maybe I should like watch these videos. Okay, so it looks like it's next Monday that they're doing. Oh, the video's already been made? Can anybody in the world watch it? Or you might have to be, oh, there.
No.
Oh, I see, it was videoed in an empty classroom. So if you want to watch this stuff for May 11th, look
The
at that.
face portrait.
I see.
Of
You can watch this. All right. But anyway, what my real point is as I said, that most of the world's interesting problems are not analytical. They do require computation with numbers, not symbols. And then hence the need to be able to do this sort of thing numerically. But these days, it's no big deal. You just sort of specify a differential equation, you watch it at the solution, and you get to play with it. And, in a way, I kind of believe, as a kind of pedagogical thing, and I'm pretty sure Dave will agree with me, as a pedagogical thing, what we really want to do is manipulate differential equations. I mean, you want to put them in your hands. I mean, you want to, not on paper, not on a chalkboard, just my belief, but you really want them kind of on your computer. You want to sort of move them, manipulate them, literally. Or else what's the point, I think is my feeling.
Yeah, totally agree.
So, but of course, courses were, you'd be surprised how, if you looked at classes at MIT, even before I was born, you'd probably find that they've added a little computer here and there, a little bit of numerical solutions, in various classes. But by and large, 90% of the material probably hasn't changed in decades. I think that's probably a fair statement. It's some sort of induction thing, well, nobody changed it a lot from the year before. And though, in the year before, nobody changed it from the year before that. And before you know it, you've gone back decades. All right, so I think that it wouldn't be appropriate to start doing any of the models like we've been doing in this class, but especially the differential equation models, because these are the ones that seem the most serious, without talking a little bit about, what is, a little bit about models. We see them in the newspaper. The models don't predict the future, and so people say sometimes that they're worthless. You may have seen some press about that. I mean, you could ask what does the public really understand when they hear about a model? I mean, you don't really find much background. So, I'll give you a view that I think is fairly common, but you get to decide for yourself. But I think that most scientists agree that a model is unlikely to predict the future, right? Unfortunately. I mean, it would be great if we could build a little mathematical crystal ball, and we could all, all of us smart MIT people could be looking into this crystal ball and really see the future. Wouldn't that be great? And that doesn't quite usually happen enough, I guess. I mean, I suppose if you throw a ball in a vacuum and you want to predict, what time it's going to fall and hit the ground, I guess the scientific models work pretty well to predict the future there. But if you want something as complicated as the pandemic that we're living through, where there's a lot of things that we just don't even know, there's a lot of data that we don't know, we haven't even done enough testing to know, what the situation is. With all the variables that we don't know, all a model can really do in most situations is help us understand general features, right? It helps us understand what's going on here. Oh, can you leave him alone? So there goes my co-teacher. Oh well, he's gone. He's been stolen. So uh, I like having his company. He really helps me. So so where was I? Yeah, models. So yeah, models are great for sort of helping us kind of understand general phenomena, and they're very, very useful in that sense. But as far as being predictive, I often find that they can't, you shouldn't expect them to be exactly predictive. You'll be sorely disappointed. That doesn't mean they're not useful, but they are, but they are mainly meant, you can really understand the mechanisms of how are things happening, if not the exact detail of what's going to happen. So I even just saw this in yesterday's newspaper. So this is from the Seattle Times, where they were comparing the Washington model with the MIT model. And I mean, I guess I could click directly onto this newspaper article if you want to see it. So, this was the Seattle Times, and they make a big deal about the fact that there's, the projected deaths in this case. It's 1573 on the Washington. Oh, this is the MIT model. The University of Washington model is a lot smaller. And this article, what I liked about this article is it actually went to the trouble of saying that, who knows, right? I mean, they make different assumptions, different things can happen, you'll get different answers, and who really knows? All right, so there's lots about that. But let me go further and let me move on from models, unless anybody wants to discuss anything about models. Dave, you want to say something about models? I would have asked Philip, but he just got taken from me.
I think we've said a lot about models during the course.
All right, so maybe this has all been said before. All right, so let me move on and talk about software for differential equations for a second. Oh, wait, this was going to come. Actually, this is going to come later. So let me actually jump right in and ask about solving a differential equation. So what does it mean to solve a differential equation? For some reason, maybe it's going to sound silly but I remember when I first learned about differential equations, I found it confusing to talk about solving it. I didn't even, maybe just the very words bothered me. I've always known from grade school, what does it mean to solve 2x plus 5 equals 11, right? I mean, we all know the answer is x equals 3 in this case, right? We know that there's some unknown x when you start your problem, right? And solving it means that there's enough information in the problem that one way or another you can find x, right? Either you can try to guess what x is, like in this case, many of you may be able to look at this and say, oh yeah, x equals 3 works. Or you can systematically go, 11 minus 5 divided by 2. Anyway, there's a procedure. And that's what it means to solve for x, right? That there's a systematic procedure that will give you the one unique x that solves this equation, right? And later on you learn about quadratic equations, and there's a systematic procedure that gives you, typically 2 x's that'll solve the equation, right? Or you can have x plus 1 equals x, and you'll never find any x that solves that equation, right? And so you all know what it means to solve that. So by now, I imagine everybody in this class has taken a basic calculus class that was supposed to have been required for this class, though I know people are coming with lots of different backgrounds, some much more advanced, some still may be taking calculus now. But in any event, we could ask for what, we could have this differential equation here, right? The unknown is x of t, right? So this is a differential equation in time, and it says that the derivative of x at time t is a multiple of x at time t, right? And of course, what it means to solve this is to find an x of t whose derivative at every time is this k times x of t. And if we know what's called an initial condition, that's a little bit more data, right? So if we actually know x of 0, so k is a parameter, and if we know x of 0, which is the initial condition, then we can solve this. And probably most of you know that here's the answer, right? And so the function of time that satisfies this derivative is the initial condition that, times a factor that grows exponentially in time with a factor k, right? So x of t is x of 0, e to the k solves this. And in most calculus classes, you would think of this as sort of a symbolic kind of operation, right? You take this thing and you plug it in. You all know how to take the derivative of this thing. You know the constant goes for the ride, the k comes out, and lo and behold, the derivative is k times what you see here. And you say, great, I know how to solve this differential equation. And in various classes like calculus in 1803, you learn these tricks that have been developed over the centuries. You may learn integrating factors, and which has always seemed very mysterious to me, except that it always works. Or you might learn other ways of getting answers. You plug in e to the lambda t or whatever, and you get an equation to solve it by magic. There are many, many symbolic magical tricks that have arrived over the many, many centuries. But I guess I still feel that the decades of pre-computer math has taken away the real essence of what is happening. And by the way, the real essence is pre-computer. The mathematicians and physicists who worked with differential equations, even back to Newton's time, did not think of it symbolically. They actually thought of it more like what a computer is doing now. Of course, they didn't have computers, but the mechanism of how a differential equation evolves was exactly how the early pioneers of differential equations thought about it. And so in a way, all those tricks that came about are kind of almost like a packaging of tricks meant to keep undergraduates busy solving differential equations, if you will. I'm sorry, it's just how I feel. But it was not sort of like the real essence of what was going on. So let me try to, give a little bit of the feel for the essence. Again, you may have seen this before, but maybe many of you have not. But let's think about the mechanism that's implied by, not symbolically, right? Don't try to take a symbolic derivative like you were using Mathematica or something. But let's try to think of this as sort of like something physical or something numerically that's evolving. And so what I'd like to do.
Alan, can you make it a full screen or something?
Oh, is it not big enough? Okay, I can certainly do that. So let's see.
The text gets quite small.
The text is getting small, I agree. Okay, let's.
Just like slide view or whatever it's called, slideshow.
If I do this.
Oh, that's good, yeah.
The only bad thing is I may have trouble finding if I want to go to some other web page, but there we go. That's better?
Yeah, thanks.
Sure. Okay, so what I want to do is I want to discretize time. All right? I'm going to discretize time by taking steps that are multiples of a step size h. I like my h to be like, I mean, it doesn't have to be this way, but like, I like to think of taking n to be like 1,000 or 10,000. And so my step sizes will be 1 over 1,000 or 1 over 10, like 0.0001 or something like that. And then what I'm going to do is my time is going to be h, 2h, and so forth, all the way up to, well, if I stopped at 1, it would be nh. If I stopped at 2, there'd be 2nh. If I stopped at 100, it would be 100 nh, right? I mean, I could keep on going forever. So I want to take time steps in multiples of h. And so just to keep it straight, my time will be an integer m multiple of h. So if you use the most common approximation to the derivative, right? If you use the most common approximation to the derivative, then you know what it is. You draw the slope of the tangent, whatever you want to call it. You evaluate x at your later time, like, this is your rate of change. You all know what that is. X of t plus h minus x of t is your change in x, which happens in a little time period h. And so let's use this approximation in our differential equation. So here our differential equation was x prime equals kxt, right? So what we now are going to do is we're going to substitute where I had x prime of t. I'm going to use the approximate. I'm going to use this red thing. And if I do that, my x of t appears in two places. It appears here, and it appears in x prime of t, right? And so I can sort of pull it all out. I think you could do this yourself. If somebody wants me to, I can write it out with the annotate, but I think you could do this yourself. It's kind of very similar to something that Dave's already done in the class anyway. And so we get this way of advancing forward, right? X of t plus h is related to, you know, the x of t by 1 plus hk. And so if this is advancing one time step, right? And so you could think about this, right? X of h is 1 plus h x of 0. X of 2h is, right, is 1, right, is 1 plus hk times squared times x of 0, and so forth. So x of mh will be 1 plus hk m x of 0. So I thought what I would do is, this is a little bit of the reason why I didn't, but that's okay. I'll just open up a Julia. We can do this without a notebook. Oops, that's not what I want. Let's see. Where do I get a Julia? What's the best way? This is why I don't want to do this. Oh, here's a Julia. Yeah. So how do you do this, Dave? Where I want the Julia to show up here. Oh, I think I just have to hit escape. And yeah, let me just grab a Julia here. This is, I'm just going to do it in front of this, right? So here. Okay. Okay. So what were we doing? What were we doing? We were taking. We were taking. Let's take h to be, I don't know. Can we take it to be 0.001? Maybe that's okay. And should we just start with k equals 1, or should we do something more interesting? Let's do k equals 1. All right, and let's evaluate. Let's evaluate our approximate x of t, and that's equal to, what did I say it was? 1 plus hk, h times k, raised to was it t over h? Is that what it was? Raised to the t over h times, and we needed an x of 0. So what should we make x 0? Should we make that 1 as well? We could change it, so let's just start with that, just something simple. Oh no. Yeah. Let's restart the kernel, because I was playing with some fun things here. Okay, so that would be, but I think you all know that this is one where the math is already well known. I think everybody knows what's going to happen. What's going to be x of 1? Somebody want to just tell me in the chat? Not that I see the chat, but I think I can. Oh, there's the chat. If I click on this. Yeah, all right, so anybody want to tell me approximately what x of 1 will be? No idea? I don't see anything in the text, in the chat. Should I just do it? All right, then let's just do it. This is the great thing about having a computer. We can check what we get. Oh, 2.716. Now, anybody want to guess what this wants to be? We could take a smaller h.
Somebody put something in the chat. Jeremiah.
There it goes. Yes.
Suggested that it was e.
Indeed. Right, and so I should probably, yeah, and so, right, so that would be, how do you do this? It's Euler-y?
/ Euler, or just x of 1 will work.
No, I like the / Euler. Right. So this thing is heading towards e, of course. All right. So, and of course, if I changed a few things, like x0 was 5 and k was 2, and let's just keep the h like this. Then, of course, if you look at the x of 1 now, then as you might expect, this will be just like the answer I said before. This will be 5 times e. What would it be? It would be 5 times e to the k. Right? In general, it would be x0 times e to the kt, approximately. So, right, so that's k, okay, times 1. Okay, all right, so let me go back to the story here. Now, yep, that's exactly right, Olga, thank you. Yeah, so Yeah, so as n goes to infinity, 1 plus 1 over n raised to the n is indeed e. That's exactly right. And that's what's going on here. So now let me do a slightly different thing. Let's look leftward. Okay, so there's actually lots and lots of ways to solve differential equations. You could look forward as we just did. You can look backwards or leftward. And here I'm going to do it here. I'm just going to solve it very quickly. And this is too hard to see. Is that right? But I want to go back to my. All right. Well, here oops. That's what I want to do. I'm going to present it and then I'll escape it. Okay. So here, just the leftward is. I just basically played the same game. I have my differential equation. X prime is kx. And now I took my leftward looking approximation, which gives a slightly different answer, at least when h is still not 0. I mean, in the limit, it'll be the same. But here, I'm going to take x prime, and I'm going to use this red approximation, x of t minus h over h is kx of t. And then kind of solving my way around, I'll get that x of t is x of t minus h over 1 minus hk. So now what I get, if I work my way backwards to 0, I have this equation, which I can write this way. And of course, you can ask what happens as h gets smaller. And you'll see that you'll get the same answer, but it will, so let me put it again over here. Let's have my new x of t over here. So x of t now is equal to, should I call it x2 of t? Maybe not to confuse it. Should we call this, let's call it x2 of t. Sort of, this is another way of solving the equation. X2 of t is, what was it? It was x0 over 1 minus h times k. And what was I raised to? Because I have it over here. Over 1 minus hk raised to the t over h. Okay, so that's a slightly different expression. Olga on the chat might recognize that it's amounting to the same thing in a limit. Let's just check though. So if I evaluate x2 of 0, x2 of 1 rather, I get 36.95. Here I got 36.945. Here it's like 0.952. So if you only looked at the first 2 or 3 digits, you'd say, oh yeah, between friends, they're the same, right? But if you look a little closer, you'll say, well, they're not exactly the same, at least not for finite h. They look like they're heading in the same place, but they're not the same. And indeed, there are many, many ways of solving differential equations, and they are not all the same when h is finite, and they get to be the same as h is infinite. And maybe that's where the power of mathematics comes in, that they do get to be the same. So what did we just learn here? Let me go ahead and put this in present mode. So, what did we learn from these? We took 2 approximations of admittedly some very simple equations. They both march forward in time. Maybe that's something that should be very clear, that the t variable is time, you have an initial condition, and we actually know how to take, this is also like induction, right? We know how to take a step. Like if I know the value at time t, I can get the value at t plus h, right? And so if I know the value at time 0, I can go forward in time and get it at any time, right? And that's, so that's kind of characteristic, that there's this mechanism of marching forward. I don't know, I mean, how you learn differential equations, or even if you learned it yet, like it does show up a little bit in calculus classes. Certainly x prime equals kt shows up on the AP exam if some of you took AP calculus in high school. But again, you almost see like you're seeing it at all time at once symbolically. And it's that march forwarding in time that I want to emphasize, that, maybe I'm saying the obvious, maybe you all understood that already. But I do want to emphasize that it's about marching forward in time. As you saw, they give slightly different answers, at least for finite h. By the way, if I evaluated at much larger times, they would diverge a lot more. Maybe we should show you that. So let's go back here and evaluate x at 4 and evaluate x2. Yeah, let's just put them both next to each other. Let's evaluate x at 4. I'm not doing it in a good order. Dave will kill me, but here we go. So we should put them underneath each other. It's easier to compare. So you could see that already at 4, they differ in the 3rd digit. And if I go to 7, they still differ in the third digit. Eventually they'll differ. Well, eventually it's going to blow up so far that it's going to just blow up. But here they're differing still in the third digit. All right, I'll go to 14, but I may regret that. This thing is trying to get really big. So I would have thought that, maybe I would have thought eventually it would have.
But they're growing apart at a constant rate, right?
They are growing apart at a constant rate, yeah. So
I mean, it's the third digit, but it's 10 to the 16 now in size. I mean, the relative difference is the same.
Yep, that is true. Right, but the absolute difference is crazy. Maybe that's what I should have, maybe that's exactly what I probably should have done. I should have gone x of t minus, that's what I probably meant to do. X2 of t, and we can do that like for t equals 5. Or here, let's do it as a comprehension. Right, so let's go this for, let's just do this for t equals 1 to 10. What's wrong? X of t minus x2. Do I have too many parens?
4? You need 4?
Oh, yeah. Yeah, it's the absolute difference I meant to say. It does look like, by the way, the one always is probably, I bet you one is always over and the other one's under. I'm sure that's true. Okay, so enough of that nonsense. What's 10 to the 16th? But yeah, okay.
So can we, just to emphasize that this equation is supposed to be, well, not is satisfied for all t. I mean, that, when you write x prime of t equals kx of t, you need to tell me who t is. And the answer is this is true for any t. And so another way of writing that would be to just remove the t from the equation from both sides. And then this is the way it's often written as x prime equals kx. And so actually, if you think about what kind of objects are in that equation, that new equation, they're actually now what? Can we have the answer in the chat? What kind of object is x prime and what is x there? What kind of objects are those? Once we've removed the t. Does that make sense? Can we write that? Does it make sense to write that down? What does that mean?
Your question makes perfect sense.
Yeah, no, I know that, but I mean, in what sense does it make sense to write this?
Is X a 3 by 3 matrix? Is
right,
X
exactly. What kind of object is it, Matthew?
Is X a 4 by 5 by 7 array? Is X a is X a triangle or a quadrilateral? What mathematical word is Dave? What simple word is Dave hoping somebody will type in the text?
No answers. Okay.
We make it multiple choice? Oh, there we go. Thank you, Olga.
Great.
So, so X is a function, of course. All right, so let me get back to...
the function that if you put in t, it tells you what the value at time t of that function is. So this is now actually an equation, an equality between two different functions. X on the, k times x on the right-hand side, k times the function x, which is the function that takes, t to x times x, k times x of t. And on the left-hand side is another function. X prime is also a function, right? It's the function, which is the derivative of the original function everywhere. Okay, that's all I wanted to say.
So,
that's something that always confused me, so I just want to point it out.
That the thing you're looking for is a function.
Yeah.
So, as you see, they diverge in the sense of not the ratio, but their difference as time goes by. But for a fixed time, as h goes to 0, the answers converge to the same answer. And, again, a little mathematical philosophy. I hope this is allowed. But there's a lot of things in mathematics that if you kind of step aside and just ask yourself, what is it that mathematicians have done? They basically take sort of limits, and the whole thing is that no matter how you get to the limit, you get the same answer. In other words, like when we talk about area, right? Like, you have some geometric object and you can cover it with little squares. But it doesn't matter how you cover it with little squares. Or you could cover it with little, you could triangulate it in various ways. And then you could add up all the little areas. And as long as it gets little enough, you all know that there's this limit thing, which is called area, right? Or there's this limiting process of solving this thing, and it's called the solution to the differential equation. And mathematicians like to make a big deal about things where while things are discrete, the answer can vary depending on exactly how you do it. But the object, the very mathematical object, exists only when you take the limit, and it doesn't care how you got there. And so that's a lot of the power of math. Again, maybe saying obvious things, but it's kind of good to say them out loud. So let's take a better look at this very simple differential equation that I wrote out over here. So, x prime equals kx is really a pretty simple looking equation. I mean, what are simple looking differential equations? Maybe x prime equals 0 is about as simple as it gets, right? That the solution is a constant. X prime equals t, I guess, is another simple looking differential equation. There the solution's, t squared over 2 plus a constant or something. But x prime equals x is also about as simple as you can get, right? You could put the 3x or the kx if you like. But, x prime equals x is simple. Simple means that it occurs in nature, I guess, or there seems to be that tendency that the simpler something is, the more likely you'll find it everywhere, in nature, in physics, in computer models, in statistics. If it's simple, it's probably out there. That's probably some sort of folk theorem, if you will. So, and here, as you've already been seeing in some previous lectures, in the context of what we're talking about in this class, it's easy to understand the exponential growth, right? It's easy to realize that, like, the number of new infections could be proportional to the number of existing infections, right? So with nothing to stop it, that would be exponential growth, right? Like, if every time the number of new infections is the rate of infection, to be precise, right? If the rate of new infections is proportional to how much it's out there, it's easy to imagine it's exponential. I want you to think about that. I want you to get past the symbolic and and even maybe for the moment, even the number crunching, and realize that, the rich get richer, the poor get poorer, right? It's one of those kinds of things going on that if there's a lot of something, it's going to proportionally keep growing bigger, right? Or it could be decaying faster depending on the process. But that's what's kind of going on, right? And so we've all seen that in the beginning, lots and lots of models, lots and lots of physical processes grow exponentially at first, or decay exponentially if that's what they're doing at first. And certainly COVID-19 has been growing exponentially at first, right? And then other things come in to try to flatten the curve, either because people are social distancing, or because of immunities, which we hope that one can get with COVID-19. These are the various things that stop the exponential growth. But left unchecked, assuming an infinite population, right? I guess if all the people disappeared, no more humans, that would stop the exponential growth. But if there were infinitely many people to infect, and nothing to stop it, you could see why it grows exponentially. I hope that sort of intuitive understanding is as clear to all of you as the simple process of solving it on a computer or solving it symbolically, right? I hope you can kind of see it. I really do. Okay. Having said that, we are going to solve things on a computer, and there really are a ton of ways to solve these things on a computer. And interestingly enough, none of these simple it's not usually the case that these simple approximations to the derivative are the best way to solve things. And so I grabbed this table from one of the members of the Julia Lab at MIT, Chris Rukakis, who's an instructor in the math department and is for sure the world's expert on solving numerical differential equations. And he's got, I mean, there are tons of things with different, MATLAB, SciPy, sundials, I don't even know all these things. He's a big Julia fan. You could take that as you want, but there's a lot of green in the Julia column. Here's the scale: none, poor, fair, good, excellent. So you can read this if you like on your own. I guess he's been going out of his way to make sure that it's not a coincidence completely that Julia is getting some of the best differential equation solvers, because he basically spends every morning, noon, and night making sure that happens. So there are lots and lots of ways of solving these differential equations. And I'm going to sort of show you how they're solved with Julia, if you want to use the built-in packages in a minute. But before I do, I'd like to go from one variable to three variables, okay? And so there's going to be only one independent variable, time, just to keep things simple. Linear differential equations can get arbitrarily complicated, as you can imagine. But here what I'd like to do is keep it in an ordinary differential equation. That means that ordinary means there's one independent variable. So some of you might see the word partial differential equation. I'm not going to talk about that here. None of these SIR or SEIR models are partial differential equations at least not the ones that I know of. So I'm not going to talk about partial differential equations. In partial differential equations, you have things that could depend on maybe time and space, right? And so it could depend but in ordinary differential equation, things can depend on time. So just to give you an example, I could be measuring the weather at a certain point of, I'll just hold up my hand like a point in space, right? And I could be wondering, let's say I've got my favorite point in space, just one point, this point, right? And I could measure temperature or pressure, right? And those are two different things that are a function of time, right? And so I would have two functions of time, but it may be that the temperature depends on the pressure or the pressure depends on the temperature. So there's a commingling. All right, let me say that all again more simply in case that didn't make any sense. I want to set up instead of having a k parameter like I had before, I'm going to have three parameters. There's nothing special about three. I'm going to call them alpha, beta, and gamma. Okay, so alpha and beta and gamma are playing a little bit of the role like k played when I only had one variable. And I would like to solve these like coupled differential equations. X prime of t might be like minus alpha x plus beta y. Y prime of t is minus beta y plus gamma z. Z prime is minus gamma z. Now, if you find this like a little confusing, like you understood x prime is kx, but wait, how are these x, y, and z's being all mixed? I think it's good to, and I'll make it bigger as Dave asked. For some reason I'm getting, let's see if I can, there we go. I have to get something out of the way that you don't even see, the Zoom chat thing. I think it might be helpful to just understand that this set of differential equations, and I didn't even really need to put the of t. In fact, maybe Dave would tell me I shouldn't have, right? Maybe I should. I think I'm gonna, I think what I'm gonna do is get rid of the of t.
Well, no, actually, I would say you should put the t
everywhere. Is that what you tell me?
Yeah.
All right, let's put them everywhere. Maybe that's more explicit. Okay, let's do that. So if you find this confusing, let's try to turn this into something that we could write a computer program. And in fact, you could even imagine sort of in your mind what's happening. So the parameters, alpha and beta and gamma, have to be supplied, right? There might be like 2, 3, and 4. There might be 5, 12, and 13. I don't know what they are, but they have to be, their parameters are just like numbers that, that sort of like tend to stay the same throughout the calculation. Very often in this world, you don't even know what they are. And in fact, a lot of the battle with these models is to actually, the models might be actually terrifically accurate, though they usually aren't, but they could be terrifically accurate. but they depend on these parameters and nobody knows how to measure them. And so you're still kind of stuck with the unknowns. But in any event, they should be supplied if you're going to solve this thing. And just like when the one variable case, you need to supply the initial conditions, right? So like I want to know at time 0, for example, what are the values of x, y, and z, right? And so a little computer program, if you have alpha, beta, and gamma, and you have this, then you see that this computer program makes perfect sense, right? That I could start at time 0, and then I can get at time h, I could take the value at 0, and then I can just evaluate. I know, you see, I know everything on the right-hand side. I know the x and the y at 0. I know my parameters, so I can evaluate this, right? Or I can evaluate this, and I can evaluate this. And it doesn't matter that I mean, I think this bothered me also when I first learned about differential equations with more than one variable. Like, how can you have a y here? That sort of bothered me a little bit. Like, how can x depend on y? Well, why not, right? Let it, just like this, right? The y can depend on the z, right? Here the z only depends on the z. And so in fact, what you can actually do is right away, this equation can be solved already. In fact, if you want to solve things analytically, you can solve for z here, plug that in, and you can try to see if you can use one of your integrating trick parameter or whatever is to see if you can, or if you can, you may or may not be able to, I don't even know, I haven't thought about this. But
you can solve everything completely explicitly in this example.
Yeah, yeah, it's true, but as an integral, right?
Yeah.
Yeah, so it depends what you mean by explicit.
No, this is all completely, you can just do everything.
So wait, if I know z is e to the gamma t.
You can put that in there and then you
and then I can plug in and find, not so sure about that.
Yeah.
What do you think the answer is?
You have an inhomogeneous.
Yeah, but then you have the answer is an integral.
Yeah, but you can do the integral.
Oh, maybe.
You use one of your famous integrating factors.
Yeah, right, probably. Yeah, that I believe. Okay, but the key point is, who cares that you can do it? I mean, like in the pre-computer mathematics, it was a big deal that you can do it explicitly. And I'm not, I mean, maybe it's still nice to have when you can. I don't know. Maybe it doesn't matter. Maybe it does. I don't know. I think something, yeah, I'll tell you, it's nice to have, like if you're testing your software or if you want to just understand a very, very simple case completely.
But if you now add an x term into the z primed equation, then it becomes much harder.
Well, that's for sure. But okay.
That's sort of the point, right? That you can get only so far with analytical.
Correct.
Things. And then as soon as you make a small modification what seems like a small modification, suddenly you have no idea how to solve it anymore with that.
Yeah, so I sometimes like to say that like a lot of the classical, 1803 type solutions are, unstable outer perturbations. Like, you could solve this problem, but if you just perturb the problem a little bit, like, like if your professor says, I'm going to change last year's exam question because I don't want everybody to just like, get the Bibles from last year, and makes it, and accidentally puts in a function that's like, not the same, not integrable anymore, you're dead in the water. That's it. Nobody could do it. It doesn't matter how smart you are. That's another thing. I hear people say, oh, the problem becomes very difficult. No, the problem becomes impossible, right? I actually think that most of these sort of problems from like 1803 are either, you could learn to do them, I mean, most MIT students learn to do them year after year after year, or they're impossible. I don't think any of them are hard or difficult. I think they're either, you learn to do them, and then, once you really learn the techniques, they're easy or they're impossible. But people say difficult. I've never understood difficult. I think difficult means impossible. All right. So let me go now to, let me go here to this notebook that I have this great picture of contagion, which if I put this online, you can play the scene if you like with R naught. But let me show you how you can sort of use Julius packages to solve differential equations. And so here I have, I guess I'm gonna have to wait for plots now.
You just add a new line before the plots so we can see.
Sorry, what do you want me to do?
Add a new line, a blank line before the plotting commands.
Okay, we have to follow Dave's stylistic rules, or
I
right.
just find it. I just find that reading that code with that block of code there is just.
Hey,
I just don't want to do it. But
you're not
now
wrong.
suddenly I can see what the structure is.
Now you like it,
Yeah.
and but I did have a new line here and a new line here. So, but I
Yeah,
agree with you.
you did, and then yeah, you were almost there.
But this new line is.
Space in after the commas as well. But anyway,
You mean all of these spaces?
yeah, just
I
makes
don't
it
know.
easier to read, in my opinion.
So Christopher Caucus doesn't put those spaces in.
Oh,
So,
he's wrong.
well, yeah, there's that.
He's not wrong about many things, but that's one of the things he's wrong about.
So the funny thing about style, well, I think
Yeah, it's a very personal thing. Yeah.
it's a personal thing, but I think my advice to the class, to the students actually watching, is think about style. You could have your own. You don't have to agree. You could do it your way, but think about it. Don't view a computer program anymore as a thing to make work, and then when you've made it work, you're done, right? Think of it as a piece of writing, something that's worth. You don't have to agree with Dave. You don't have to whatever, but but think about it is I think the most important thing I can say about writing software. That's probably the thing to tell you the most. Um, so as I mentioned, there are lots of ways to solve differential equations, and um, you know, it becomes a black box. Something we've kind of avoided in this class, as I said at the beginning of this lecture, that in this class we really like to let you build things from scratch, so you can really understand all the moving parts.
So, sorry, can I just make a comment that what Alan was describing with the time steps just now is what you're doing on problem 1 and problem set 5, exercise 1 and problem set 5.
Yeah, so that you will be able to do it.
Yeah, that's exactly the Euler method that I'm describing in words in problem set 5. So now you actually have a very good example to follow of exactly how to do that. There's not supposed to be a mystery, right? I mean,
yeah,
there's
no.
a balance between explaining too many things and not explaining enough. And
So, but I also want to give a little bit of a. I think it is great to just use the ordinary forward differences, the rightward-looking differences, just to do it once. But I also wanted to kind of tell you the other side of the story. This is Chris Rackauckus's little blog, and of course he's saying that this thing that you're using, like the easiest discretization of a differential equation, it goes by the name of Euler's method. Probably most of you know that Euler was a mathematician from a long time ago, certainly pre-computer, and so when Euler solved it, he certainly didn't take very, very small time steps. That would not be humanly possible even for a great mathematician like Euler.
No, they did though. They did a lot of hand calculation in those days.
Not 0.00001.
Well, yeah, maybe not.
But he was a great calculator. I mean, I don't know whether he used his quill pen or what it was he used to do it, but I know that he was a remarkable. He was remarkable. But here in this little article, he actually goes and talks about why you shouldn't use it, and he compares a few different things. One of them is this TSIT5, which I don't know. I don't even know what it is, but it's some fifth order adaptive type stepping method.
It's a Rumakuta method.
Yeah, I didn't want to say the words.
It's just the name of a person. Situras is the guy who invented this method.
Okay. Okay. Situras is probably not so long ago, right?
No, it was 2011, I think.
Yeah, that's not so long ago. So, but as I said, there are many, many ways to solve differential equations. You only just saw two of the simplest. And, if you really want to know how they do it, it's not, these methods are not terribly complicated. Just usually what happens is, instead of just using my value now at t and at t plus h or t and t minus h, you could use t plus h and t plus 2h, or you could go backwards, or 9 steps forward and 10 steps backwards. You can use more information, and sometimes you can actually, without much more work, you can get a lot more accuracy or a lot more speed. In fact, I've been told that there are some, I don't want to mention any names, but I've been told by Chris Rackauckus that there are some packages out there that actually deliberately slow down the differential equation solvers so that it doesn't get plotted too fast, or something like that. I don't know why anybody would do that, but anyway.
Is that MATLAB?
I didn't say any names. Didn't say any names. This is what I was told. Oh, okay. All right. But anyway, you could see that here's a differential. Here's the differential equation being solved. So let me just sort of show you the moving parts, because it's exactly the same parts that you saw before. And so here, let's actually even use the same notation. So let's make the initial condition, let's call it x0. Okay, so there's the initial condition, and there's the k, right? And so the initial condition finds its way here. Okay, so f of x pt is k. Can I make the k like this? I don't know if this would work. Something tells me it won't work. Does this work? I have a bad feeling this won't work.
Yeah, it should do.
Should it? All right, maybe it works. Why am I scared it won't work? Maybe I'm just a pessimist.
But did you pass the right thing in?
Well, I don't know.
Oh, no, you have to extract the first.
Yeah, that's what I was afraid of. Yeah, that I would have to go.
But you didn't pass in the parameter ever. You have to pass in the parameter in the ODE problem.
All right, well, k was 1, right? So I'd have to, wait, so how would I do it?
Passing it as k, it's going to use the local variable k now. So you just need to pass k into the ODE problem.
Oh, wait, so if I go like this,
and then put,
I know what you're saying. ODE problem, wait, where do I do it?
Yeah.
As another parameter?
Yeah.
That I believe, that might just work. Maybe this is a little simpler to understand. All right, let's do that. Yeah, okay. So, yeah, so here's this is the function that is the derivative, right? So this is, I can put a little comment here. This is your x prime of t, right? So you just put whatever x prime that you like.
So x prime of t equals f of x t, basically.
You want me to write that? Okay, equals f of x k t. And I'll just say f of function parameter, time, something like that. I don't know if that's the best way to say it, but there it is. Okay, and I'm just going to, the t span, the time span will be from 0 to 3, which you can see over here. You could change that, right? And the problem now has all the data in it. It's right. It's got the function. It's got the initial condition. It's got the time span, and it's got the parameter.
And it's just missing some spaces after the commas.
Oh, yes.
This is actually defining a new object of type ODE problem. So this is a type that's defined in the package, just like we've been defining types. And you can see what's in, right? So they define a special way to display objects of this type. So inside that object, there are lots of things stored, and it has a very complicated type, but basically it just contains the information that we just gave it about, what kind of function it is, what the time span is, what the initial condition is, what all the types of everything is. So
this is fancy Julia that you see all the time. People create a new type and they do some cool things with it and they move it around. And when Julia works right, all of these things come together and things just, things that you write here just work over there, even if you wouldn't expect them to. So like in the old days, people would talk about, if you want things to work together, you have a spec and then somebody has to solve the spec. But in Julia, we want to make that not even necessary anymore.
Well, there's implicit spec here, right?
I suppose. Okay, so there's the problem. And of course, I put a manipulator around the same thing. I didn't have the K, but I just put a manipulator around this whole thing, and so we can play with it. And of course, everything is much more fun with manipulate. And as soon as this thing compiles, what I'm going to do next is show you how easy it is to. We started with a differential equation where we know the answer, and just how easy it is to turn this into a differential equation where we don't know the answer. In fact, in just a minute, I'll do something like, I don't know, what would be a good thing to do? I'll add, 0.01 times sine of x or something. Right, something that you probably, I don't know if that's easy. You might say there's an integrating factor there too. But here, let's...
I mean, first order differential equations can always be solved.
Yeah.
For an integral, right?
But, yeah, so here, so here I'm changing the initial condition. It can go up and it could go down, right? I could change the growth rate. Right, and so it's fun. This is what I feel, this is the thing that I wanted to really say, that this is what you should be doing in every problem set in a course like 1803, if I had my way. You just keep doing this and you would really understand, what the solutions really look like.
There's even a book that does that.
I'm not surprised.
Nick Trevethan has a book called Exploring ODEs, which is a great
book.
About that,
yes.
I totally recommend it, but except that it uses MATLAB, which is obviously just terrible.
There's a Euro project. Rewrite the whole thing in Julia, and then it'll be much nicer. So should I let on the Nick Trevethan story? Yeah, let's find the book there. What's it? Nick Trevethan. ODE, what's the name of this book? Numerical ODE textbook, is that it? Exploring ODEs?
Yeah.
So freely available, you can download a copy if you want. There it is. So perhaps I'll mention that Nick Trevethan was my PhD thesis advisor. He was at MIT back in the day. He moved to Oxford at one point. And the fact of the matter is, he bought the very first commercial copy of MATLAB. The very first, copy number 1 from the MathWorks. And the day it arrived, it came all shrink wrapped. Back in those days, software arrived on disks of some kind. I don't know if you guys have even seen disks, but anyway, they came on disk. And he handed it to me. And there was a PC in the basement and said, give it a try. And so I actually was the very first user of commercial MATLAB in the world. And I know that because I had the first copy in my hands and shrink wrapped. I think I was the one who peeled the plastic on the first copy of MATLAB. Came with a little disk and a little book with, I don't know, it had like a dozen commands, like CumSum, I think was one of them, and plot, I think was also. And yeah, I don't have MATLAB anymore. I removed it from all my computers.
They apparently have the SIR model in 6 lines of code, which is just what we're about to do.
They have it in there?
Yeah, in chapter 10.
Oh, should we look at that just for fun?
Could do.
Should we look at some MATLAB code?
I mean, it doesn't look that different from Julia, except they have all these.
Do you know the page number? Or what's the quickest way?
No, it's chapter 10. It was in the contents page. I just noticed it.
All right, I'm in chapter 7, chapter 8. There's 3 pictures, which is maybe the whole point. Maybe, that Nick and I would certainly agree that that's what differential equation should be. That you generate lots of pictures. So let's find, we haven't shown them the SIR, but anyway, it's here somewhere. I guess I recognize it when I saw it. Here we go, SIR model for epidemics. So we're going to see these equations in just a minute.
There it is. That's the code.
Look at it, you have to actually spell out beta. That's already scary to me. Oh, it's using ChebFun. So,
yeah, the whole book is
of course he's using ChebFun. So with the proxfun, which is Julia's generalized thingy rather, we could do that too, right?
Yep.
So maybe we should do that. Okay, let's, we only have like 20 more minutes, so let's, 10 more minutes, so that's even worse. Let's cut to the chase here. Okay, so yeah, if we can manipulate these things, and Chris has really been selling me on the modeling toolkit. So, I have to read it again. I have this redefinition of X. But if I read, I'm sorry I called it X, but now I'm gonna have to do using plots again. But while I'm doing using plots, I can put in spaces that Dave's gonna insist on. So like this one. So the idea here is you just basically specify both your parameters and your independent variable, and what does the derivative mean, right? So the derivative, it's these weird twiddles, but here this is basically, whoops. What's going on here is that just to, I mean, if you just, I mean, I just mimic this stuff, but basically what's going on here is, oh, sorry, this one. I want to do this one first. What's going on here is this is really just that. It's x prime is equal to minus kx, right? And so you just write derivative is minus kx, you specify the initial condition, you specify the parameter, and bump, you'll get the solution. And while I'm waiting for it to compile, let me just show you that once you sort of have the basic framework for solving this, I mean, I've got to admit, I like solving things in 3 lines as well. I mean, it's not exactly always what happens in Julia. Not everybody agrees, but there is something wonderful about solving things in 3 lines.
I mean, it's 3 lines if you put things on the same line.
Yeah, I know. He cheated a little bit, right?
Well, that's what he does.
Sorry?
That's what they do in the book. That's why it's 6 lines.
But he does put things on the same line that arguably are units. They're chunks, right? So maybe it's not so bad to do that. In any event, what I was going to say is that if you want to add more parameters, not just the k, but if you want to have alpha, beta, and gamma, and you don't want to have more functions of time, not just x, you could have x of t, y of t, and z of t. You can take that problem that I just put on my slides over here and solve it, and you'll also get the solution. So how long am I going to have to wait for the solution? I guess I'm recompiling both the plots, the modeling, well, the plots, the modeling toolkit, and the differential equations.
Yes.
So that might take just a little bit of time. So maybe what I'll do is also move forward. Oh, here we're getting some plots. This one I actually did first. This is the solution to the XYZ problem that I had put up on my slides. Okay, and here's the solution to just the exponential. All right, but now let's move forward and do an honest to goodness SIR model. So here's an SIR model. And let's talk about the SIR model. I don't know, Dave, you also said you had one. Maybe I'll just start by explaining what's going on, and if you want to show your model too, we can. But basically, we could go to the Wikipedia article as well. It's basically the same thing, where people are susceptible, infectious, or recovered. Okay, and the way to understand this model is, again, we have these 3 differential equations. Some people divide by n and they talk about the percentage of the population. Some people do absolute numbers. This is written here as absolute numbers. But basically what this is saying is the interesting term is here. It says that, first of all, just to sort of talk our way through it, we see that the susceptible population is, the rate is negative, okay? That means that one way or another, people are going to move. The population starts out as being all susceptible, and what's going to happen is they are going to get infected, right? It's going to go down. It doesn't mean they'll go to 0, but people are going to get infected. That's what that minus sign here is. The recovered, by the way, is positive, right? That's always a good thing. So ultimately, the amount of people, the recovered population is going to go up, right? And it's going to go up at this rate gamma, right? It's going to depend on gamma times the infected. So let's look a little bit more closely. If you could imagine that, every infected person meets up in every time step with beta people, then you might think, oh, okay, then I'm going to infect, then the number of infected people will be this number here. Can I use my annotate here? Let's do that annotate thing. Yeah, so let me look at just this piece of the term. In fact, at t equals 0, at time 0, everybody's susceptible. S is equal to n. Everybody's susceptible in the beginning, and so this thing is just 1 at the early stage. right? This is just one when you start out. So if everybody who's infected meets beta people, then this would become the rate of infection. Now later on, and of course, if you assume, yeah, there's a couple of ifs here, but let's assume that you meet beta people during your time step, and you just infect everybody you meet. Okay, this is what you would see. Okay, another way to say it is that you actually meet a lot more people, but beta is the number of people you're going to infect when you meet everybody. That also works just as well. So that you don't have to infect everybody you meet, you can maybe just infect 80% of the people you meet or 10% of the people you meet. You can fold that into the beta. But it's also the case that if you're infected, you're only going to infect not everybody you meet, just the susceptible people. The other people are already infected. And so this is like the probability, right? So S over N, I could write it over here, right? So S over N is like the probability of a person being susceptible. Person you meet being susceptible. All right, and again, the beta is equal to the number of people you meet and infect and can infect per unit time. All right, so that's the beta model and the SAR model, and the gamma is the rate of recovery. So I hope you can understand. It should be very simple to understand. What's going on in the second equation is here are the people who we lost from the susceptible population becoming infected, right? And here are the people recovering, right? So minus gamma I is a rate of recovery. Okay, and then finally, the people from there go into here. Does that make sense? Happy to take any questions, but just to kind of show it being solved. So let's do that to show it being solved. Here you could see a typical scenario where people all start out susceptible, okay, but then that goes down. The infections go up for a while. This is that exponential growth. In fact, you could actually analyze it using techniques you learned in 1803 or 1806 for a little while. These would be linear, but then eventually the nonlinearities come in. And then finally, here's the recoveries, right? Actually, if you add up S plus I plus R, you would actually get a constant population. So
can I just say something? So you should recognize these curves because they're the curves you should have, basically they're almost the same as the curves you should have got out of your own simulations in problem set 3, say. Because what this differential equation is actually doing is describing the way that the means of, this is one of the questions on the problem set, the mean of the stochastic model that you were working on as a function of time basically correspond to these differential equations in some approximation.
Yeah, so you might say that the differential equations kind of very efficiently don't require the random, the Monte Carlo simulations. You don't have to do the random bumping around. And it sort of lets you track the average directly. Because all those Monte Carlo simulations take a lot of computer resources. And the evolving, if it's okay to just evolve the average, then you can use a lot less computer resources and thereby analyze a lot more situations. So in a way, the Monte Carlo simulations are kind of fun because they feel very explicit that it almost feels like a real epidemic evolving.
Well, especially when you include the space, which is even harder to do in these differential equations, right?
Yeah, I guess the beta just sort of kind of has the entire sort of, who you're meeting nearby kind of just stuck in one number. That's all it does. So I'm out of time. I'll just mention, I guess I'll put this notebook up a little bit later, but the SEIR model just has a couple of more parameters, a couple more rates. It has the it has mu people being born. So here, for example, the susceptible population, this term says that mu little babies are being born every time, and so they enter the susceptible pool. Here we have the rate of birth equals the rate of death, and so minus mu s says that these susceptible people are dying without entering the other states. And this is the same as the SIR model, which is saying you're becoming exposed, right? And so here it is here. And then similarly here, you can go from exposed with the A down to the infected, or with the mu, you can just die off. Similarly here, with the mu, you can die off from being infected, or you can go on to being recovered. But even recovered, you can as well just die off and disappear from the population, right? And so it's just a more complicated model, but we can run this one as well quickly before I end. Hopefully it won't take too long. And again, you can see the same basic sorts of curves where first people get exposed, but that dies out, infected like this, and then finally they're all recovering over here. All right, lots of good stuff in the differential equation models. So I hope we were able to, whether you've seen differential equations or not, I hope you've been able to sort of work your way towards going from the, the most basics to, the very real models that lots of people are talking about these days. These are models, they're still quite simple. The fancy people are doing much more complicated things, but a lot of people are talking about these basic kinds of models. So see you all on Wednesday, and I'll get all this stuff going. All right, bye-bye.